Hey everybody, welcome back. It's Dr. Jacobs again. This week we're going to be learning about the normal curve, the area under the curve, and standard scores. So let's go ahead and get started. All right, so this week we have some unit learning objectives, and these are things that I want you to be able to do before you're out of this unit. So I want you to be able to explain what the normal curve is in your own words. I want you to be able to describe the three major features of normal curves. I want you to be able to define standard score in your own words and calculate a standard score presented in the chapter accurately. So we're going to learn about the z-scores. I want you to be able to list the percentage of scores that fall between the z-scores on a standardized normal curve. I want you to use the z-table, in other words, the area under the curve table, and z-scores to solve an array of word problems. I want you to be able to utilize your understanding of z-scores to identify outliers based off of the plus or minus 3.29 z-score criterion. And then I want you to identify how to test the assumption that the population distribution is normally distributed. Okay, so we're going to go ahead and get started. For this unit, you're going to need a couple of worksheets. So in our folder, you'll have a worksheet. It's not going to let you see it because everything's blurry. I have the blur background on from a different meeting. There will be an area under the curve table. It's also called the Z critical value table. And I've got to figure out how to get rid of that blur because I will not be able to show you things if I need to later. We'll worry about that. It will be future us problem. And then you'll also need the worksheet called area under the curve practice examples because we're going to work through those in this unit. All right, let's go ahead and get started. So I always like to start this unit with this quote from Sir Francis Galton, because I think it's actually a really beautiful quote. It has a bunch of fancy words. So we're going to read it and then we're going to slowly interpret what it means. All right, so whenever a large sample of chaotic elements are taken in hand and marshaled in the magnitude, or in the order of their magnitude, an unsuspected and most beautiful form of regularity proves to have been latent all along. Sir Francis Galton. And so the reason why it's really, really neat is if we break down and see what this really means. And it's saying that sometimes in life, or most of the time in life, it looks like when you have a large sample of things that they're chaotic and they're not, they don't have any order, there's no meaning in it. But if we take all of that chaos and we put it in order of size, something really beautiful happens. Almost every natural phenomenon has the same shape or this normal curve, but it was hidden amongst the chaos. And I think that's really gorgeous. All right, so that leads us, and what Sir Francis Galton was talking about in that quote is the normal curve. And this is going to be an extension of what we learned about in our last unit. Okay, so the normal curve, though, is a theoretical curve that gets its shape from a specific mathematical equation. So maybe you've had like a calculus class, maybe not, or classes where you have to graph lines, right? Like with calculus, they do limits and things like that. But we know that if we have an equation that it can create a different type of line, a different shape of a line, depending on what it is. And the normal curve is one of those. It's basically a mathematical equation that gives you a shape that looks like this. It is a theoretical thing. It is not a real thing. It is actually just an abstract principle that isn't in real life, which can be very confusing because we don't like abstract things as humans. And so that can be really hard to understand only because, sorry, I am trying to figure out how to get this blur off of my sad thing. There we go. Do not blur my background. We are problem solvers here. Now I got to get the things back to where they were. There we go, so I can see it. So this is a theoretical, it's abstract. Humans don't like that. That's why a lot of times you'll have me give you some metaphors and things like that. And so when we see the normal curve, we're actually going to be using this when we start doing our inferential statistics throughout the rest of the book once we get after our chapter 7 that teaches us the hypothesis testing steps. So sometimes you'll hear this curve referred to as the bell curve. There was a super controversial book called The Bell Curve. I've never read it. I just know that it was super controversial. And so when we see a normal curve, so when we're doing some of these inferential statistics and things, I'll actually have you draw out a normal curve shape, and you'll get to see an example of that coming up here. And when you see that normal curve shape, I want you to remember that there's data that falls under these normal curves. So in the last unit, we built histograms with the little different bars, and we could draw a line over each of them to try to tell the shape of our distribution. So a normal curve, if we have a normal curve, it's the data that's underneath there is actually normally distributed. And so that is a very sad normal curve that I drew there. They're actually supposed to be beautiful and symmetrical. You've probably seen it before. This is why I am your stats professor and not your graphic design or art teacher. And so the three features of the normal curve, or the three characteristics, is that it's unimodal, right? So when we look at the normal curve, what does unimodal mean again? If you said that means it has one mode, you're right. So if we have the normal distribution, it only has one hump. It's also symmetrical. So my picture is not the best example of that, but you should be able to fold it in half and it look exactly the same on both sides. And then it's also, this one's the tough one for students to remember most of the time. It's also asymptotic. And what that means is you can see there that the tails of our normal curve, they can get infinitely close to that x-axis, but they will never cross the x-axis. Okay, and so this will tie in with some other things, and we will get back to using the normal curve and how this fits in, but we need a discussion about something called standard scores first. So standard scores are scores that we can calculate so that we can compare scores on different measures. Okay, so if you took a test in stats class and you took a test in your history class and you wanted to compare those scores, you can't do that with the raw scores that you got on the test. What you would need to do is to convert it into something called a standard score, and I'm going to teach you one of those. In this lecture itself, you would have to convert them to some sort of standard score so you could get them on the same scale. All right, so some example standard scores are the z-score, the t-score, and I'm going to teach you how to do the z-score for this class. So our z-score formula, so any z-score equals your observed score or your x, right? So x minus the mean divided by standard deviation. Now think about this for a minute. Don't put this answer in the comments or anything so that people can learn from this too. What is familiar about this formula? Again, don't write it as a comment. Let people have this as a learning opportunity, but pause this and really think about this. If we're looking at this formula, what is something in here that we've already done? If you said we've done x minus the mean before, and that's a deviation score, you're 100% correct. So what we're looking here is we're finding the deviation scores for each for our data, and then we're dividing it by the standard deviation. And so what that does is when we divide by that standard deviation, we're seeing how far a score is away from the mean in the number of standard deviations away. And so I'm going to show you the formula and symbol so it makes a little bit more sense. So we see there that we have Z, which is going to be our symbol for z-score. It'll also be our symbol when we move on later to something called a one sample z-test. So this will be for two different things. But for this unit, this is our symbol for z-score, equals x minus the mean. So x minus the mean, we've done that before, that's a deviation score, divided by, and you'll see here we have s sub x, and what that's saying is it's the standard deviation of your x's. And so all we're trying to see here is how many standard deviations is your score away from the mean. That is what a z-score is. Okay, so that's a much prettier looking normal curve there, and we'll see in the center there I have a little line in the middle. That's where our mean is. That's where a z-score equals 0, because if your x value equaled whatever your mean was, it would be 0 standard deviations away from the mean. Okay, so here's the formula again. Z equals observed score minus the mean divided by standard deviation. What would the z-score equal at the mean again? It would equal 0 always, right? Because if we have our x minus the mean and they're both the same, 10 minus 10 equals 0 every single time. So the mean, like we saw on the previous picture, is always going to be in the center. So what levels of measurement must our data set be in order to calculate z-scores, and why? So think about this question. What levels of measurement should our data set or our X's in our data set be in order to calculate Z-scores and why? So what I want you to do is to pause me real quick, think about it, actually answer this, try to answer this in your notes, and then come back to me. Okay, it is a scale data. And so that would be either interval or ratio level of measurement. But why is that? If you said because in order to calculate the mean, right, and standard deviation, the values have to be on an interval or ratio level of measurement, you're absolutely correct. And so earlier when I said that we would keep seeing some of these things over and over again with these levels of measurement, we're going to continue to see this pretty much for every unit throughout the rest of the semester. There might be one unit that doesn't do that, but it's going to be very, very limited. So Z-score example. So if you have a mean of 100 and a standard deviation of 10, what is the Z-score for the score of 110? And I want you to go ahead and do this in your notes right now and then check your answer. It would be +1. And so the way to think about it, remember, our Z-score is just telling us how many standard deviations away from the mean your X value is. So here, if we have a mean of 100, our standard deviation is 10, we can see that if you have a X value of 110, that the Z-score for that's going to be 1 because it is 1 standard deviation to the right of the mean. So then let's try this again using that formula where we have Z equals X minus X bar, all divided by the standard deviation. What would be the Z-score for a score of 90? Go ahead and work that out in your notebook now. So if you said it was a -1 because it is 1 standard deviation smaller than the mean, you are correct. All right, so temperature example here, we can see here, let's pretend that the mean temperature outside where you live was 70 degrees Fahrenheit, okay? And the standard deviation of the temperature was 5 degrees Fahrenheit over the course of a calendar year. You'll notice in this little example that Z-scores can be both positive and negative. So all the positives and negatives tell you is whether it is to the right of the mean, and they'll be positive if that is, and then or negative, which means it'll be to the left of the mean. So if we wanted to know what the Z-score was for 80 degrees Fahrenheit, you would plug those numbers in the formula. So you would have Z equals, in the numerator, you'd have 80 minus 70, and then you'd have it divided by 5 in the denominator, and then you'd have 10 divided by 5 would be 2, okay? And so if we look at this, if we look at the mean temperature of 70, we see right there in the middle, it's 70. If we went to 2 standard deviations to the right, so 1 standard deviation is equal to 5 degrees, right? And then if we go over another one, we see that it is a score of 80 is 10 degrees or 2 standard deviations to the right of the mean. So it's telling us the same information that we're learning with those deviation scores, except for it's just putting it in a different unit, right? Which is our standard deviation. All right, so we have our standardized normal curve. And what this is this is a normal curve where all of our raw values or X values have been transformed into Z-scores. And this allows us to put our data in this form so that we know what percentages of our data set fall between which particular Z-scores. So for example, and I'm going to teach you what this is in a minute, but we know what percentage of our data set falls from a 0 to a Z-score of 0 to +1. We know what percentage of our data falls from negative Z-score of -1 to +1. We have these values, okay? And we will move on to that pretty soon here. So like I said before, though, anytime you see that normal curve, what do I want you to remember that falls underneath that? If you said data, you're right. And with this class, we're interested in what this data looks like with humans. So I drew you a little cute picture of a normal curve with little humans under it. It kind of looks like the 2 on the ends are trying to run away. And since the normal curve is asymptotic, I guess they'll run forever because it'll never actually close off. So they're trying to escape. So here's this normal curve. I told you all that we'd be able to see what percentage of data fell between which z-scores. This never changes. So this is really important that when you're looking at this and when you're reading this, these are some of the things I asked you to memorize, right? So if we go back to the unit learning objectives, I want you to tell me what percentage of the data falls between each of the z-scores. So here we see from a 0 to a +1 that always 34.13% of our data set is going to fall under or between a z-score of 0 and to a +1. Something that you'll notice that's interesting is that we remember from the features of our normal curve that one of the features is that it was symmetrical. And so if we fold our normal curve in half, we'll see that it has the same exact values between the different z-scores. So 34.13% falls between a z-score of 0 and +1. And it also falls between 34.13% of our sample or data falls between a z-score of 0 and -1. Okay, so you should be able to memorize these. You should know that between a z-score of 0 and 1, +1, it's 34.13%. Between a z-score of +1 and +2, we have 13.59%. And between a z-score of 2 to a z-score of 3, we have 2.14%. Okay, so it's going to be important that we're able to convert proportions to percentages really quickly. I typically tell you all there's no math. The only caveat that I said is that sometimes I might have you convert proportions to percentages and percentages to proportions because I don't consider that math. It's something you can just move the decimal over and add a percentage sign. So let's practice that again. How do we convert the proportion 0.97 to a percentage? What do we do again? All we got to do is multiply our proportion by 100 and add a percentage sign to it to turn it into a percentage. Therefore, what does a proportion of 1.00 equal to in a percentage form? It equals 100%. So let's try to flip it around. What if we had a percentage of 88%? What is that if you convert it back into a proportion? You said 0.88. You are correct. Okay, so there is a Z table I told you all to have. You couldn't see in the beginning of this little video because I had my blur background on. So you'll want this table. You'll actually probably want to print it if you have a notebook of stuff. You might be able to get away with just having it on your computer, but it might make it a little bit harder to see what we're doing while we're working through these examples. I do have some screenshots in here so that we can practice this and see what it is here, but you will need to be using this for class as well for later assignments and things, so you might want to just print it off. You will actually get other critical value tables throughout this class, so you might want to highlight that it's the Z critical value table up at the top. So if you read the top there, it says which table it is. All these tables might start kind of blurring together, so you might want to write yourself a note that that's the Z table, or just highlight where it says that in there. So when we look at this table, I will teach you how to interpret this. We have that first column labeled z-scores. These are the individual z-scores that it could be. So those are just z-scores in that column. So you will use the magnitude of the z-score for the z-score column. So you'll notice in the actual critical value table that I made that there's no negative numbers on that. And that is because we're just looking at whatever the absolute value is, just the size of it. The negative and positive with z-scores just tells us if it's to left or right of the mean. And we know that the normal curve is symmetrical, so those proportions all will be the same. Okay, so then we have an area that says the area between the mean and z. If we drew this out, if we drew out a normal curve, I'm going to write on this if I can find a pen in my office. Found a Sharpie and a notebook. That will work. So actually I found a pen. There we go. That's exciting. So if we draw out our normal curve, sometimes that helps to show or demonstrate what this means. So here I drew my normal curve. Where is the mean on the normal curve again? Do you remember? Where did we put that mean? You said it falls right in the middle. You're correct. And you'll see that there, I kind of put a little mark there to show us that that's going to be the mean. This pen is kind of being leaky, but it'll have to do. So our mean is always in the middle right there. And then, so when we see the area between the mean and Z, we can plot Z-scores onto here. So let's say we have a Z-score of a 1. You'll see because it was positive, it's to the right of the mean. And so when we had the area between the mean and Z, this is the area under our normal curve that we had. And it's between the mean that we just had and whatever Z-score we're looking at. So if you see here, when we're talking about the area between the mean and Z, we're talking about the area that is between whatever our mean is and the Z-score that we're looking at. And what we have in that column is those are actually proportions. So what we see there is that between the mean and Z score of 0.02, that only 0.0080 proportion of our data falls into that. If we convert that number into a percentage, we see that 0.8% of our data set falls between the mean and a Z score of 0.02. So we also have something called the area beyond Z. This is the area under the curve that starts at the Z-score and goes away from the mean. So this is kind of opposite what we just did. I'm going to draw out another normal curve. I'm going to label this other one. So this other one's called the area beyond Z. So you'll draw your normal curve. So you'll see here, I have a new normal curve. We're going to put, I always like to put the little tick mark where the mean is. When we move on later, we'll label that likely as something else, but we'll always know that the mean's there no matter what. If we still use the Z-score of equals 1, the area beyond Z is the proportion of our data that is at that Z-score and moves away from the mean. So here we see we had the area beyond Z. These might be good things that you put into your notes because we're actually going to use this table and this understanding to solve some more problems in this unit, which will help give us a rationale for how we use these critical value tables when we're doing inferential statistics. Okay. So what are the decimals in the area between the mean and Z and the area beyond Z columns again? That's right. Those are those proportions. All right, so we can see here that the area between the mean and Z, again, is we're going to be looking at that mean and then whatever Z-score we're interested in learning. And for example, on this beautifully drawn image that I made you, we are looking to see what the area between the mean and Z of a negative 1.25 Z-score was. So we remember that with this, that these only have the absolute values of the Z-score. So we would look up to find the area between the mean and Z-score of negative 1.25. In our chart, we'd look for a Z-score of 1.25. So go ahead and locate that in your chart now, or your table. Then we move over to the area between the mean and Z to see what the proportion is. We see in our table that it's what proportion? It's 0.3944. Okay, so if we want to convert that proportion into a percentage, we know that 39.44% of our data is going to fall between the mean and a Z-score of negative 1.25. So negative numbers can be really difficult for people to understand because they're also kind of another abstract thing, and we deal a lot more with positive numbers than we do with negative numbers. So I drew this little number line to remind you that as the numbers move away from 0, they actually get smaller. And sometimes that confuses students because they're like, wait, what? -7 smaller than -1? Yeah, because it's moving further away from 0. And with that, people get confused, I think, because the actual number piece is bigger, but once you add that negative sign, it actually makes it smaller. All right, so then the area beyond Z again, if we want to look for the area beyond Z of a Z-score of 2, If we want to look back in our table, and I don't actually have this written out in our PowerPoint, but if we wanted to solve for this, what would we do first? What would we need to locate in our table first? If you said we needed to locate a z-score of 2, you're correct. So let's go in our little handy table. Look for a z-score of 2. Okay, and if we're looking for area beyond z, then we look in the area beyond z column, which we see the proportion there is what? If you said 0.0228, you're correct. If we convert that proportion into a percentage, we see that 2.28% of our data set falls beyond a z-score of 2. All right. So for this, we can actually use these different types of understanding to solve different practical problems. So I actually have a handout for you in our folder that I want you to have. If you can print it out, please do, so that you can write on it and go through this example while I'm going through it with you in this lecture. That will help you understand what we're doing a lot more, because you'll be responsible for knowing how to do this later on. All right, so the example is 200 health science majors need to take a statistics class. In order to take the course, they were required to take a prerequisite mathematics exam to see if they had all the prerequisite knowledge necessary to be successful. So let's say this test had a mean of 100 and a standard deviation of 15. If UCM decided to allow the students with scores of 115 or higher to go into an advanced statistics research design class, how many of these students would have that option? Okay, so hopefully you have the paper printed out so we can go through this even with me going on to the next slide. So we got to think about, what's our first step going to be? What do we need to do to solve this problem? What kind of information do we have? Okay, so our first step for this is going to be to find the z-score. Okay, so we remember our formula for a z-score is what? If you said it is z equals x minus x bar, you're correct. All right, so let's solve for this problem. Okay, so what you need to do on your worksheet is write the formula for z-score. So we know z equals x minus x bar in the numerator divided by our standard deviation of x. Here we know from our thing at the top, we need to look and see what is the information that's important in here. So look through this and think about what information in this problem is vital for us solving it. All right, so if you said, well, we are looking for a z-score associated with a score of 115 or higher, so our x is going to be 115, minus our mean, which we know is 100 from that problem, divided by the standard deviation, which we know is 15. So then we go through and we write this out step by step so that we're showing all of our math. So 115 minus 100 is 15 divided by 15. Notice that I am showing all of my work as we work through this. And when we take 15 divided by 15, we see that we have a z-score of 1. Okay, so our first step is figuring out what that z-score is, and we did that. Well, crud, how do we solve this problem? We know that a score of 115 or higher is associated, or a score of 115 or higher is associated with a z-score of 1. Our next step then is going to be to draw out that normal curve, and we're going to use this information to try to figure out how much data falls under the curve in that certain area, like how many students would be able to. So I draw out my normal curve. We know we have a z-score of 1. So go ahead and do that, and then I'm going to show you the answer, but make sure you pause me and do this first before you look at the answer. All right, so you see there we have our normal curve. I have a z equals 1. And we're wanting to know how many students can take this class. So we know that we have a sample size of how many of these health science majors do we have? So it's in the information for that is in the problem itself. So look at that real quick. You said 200, you're correct. And so we need to know right now, do we want to find the area between the mean and Z, or the area beyond Z if we're looking for the students who get a score of 115 or higher? If you said we want to find the area beyond Z, you're correct. So if we look here, we're looking for the area beyond Z because this is a score of X of 115, and we want to see who got that score or higher. So if we want to know what proportion of our data set falls beyond a Z-score of 1, we have to go to our handy dandy little sheet, and we're going to look up a Z-score of 1. So go ahead and do that now. Okay, so then we want to look in the column of the area beyond Z to see what the proportion of our data set that falls beyond Z. Go ahead and do that now. If you got the area beyond Z equals 0.1587, that's correct. You might be tempted to convert this into a percentage right now. I actually wouldn't do that. We also will not round these proportions in this table. It's one of the few times we're not going to round to 2 places past the decimal. We're going to leave it like that because we know that 15.87% of our data set falls beyond a Z-score of 1. And we know that we have 200 health science majors. So it's easier to keep it in proportion form, because if we want to find out what 15.87% of 200 is, what would we do? If you said we had multiplied the proportion 0.1587 by 200, you're correct. So if you see, I'm showing all of my work for this, and we're to this point, we're going to multiply 200 by 0.1587. And when we do that, what do we get? When we do that math, we get that it is equal to 31.74. So if we go back and see the question that we're trying to answer, we're saying, hey, if UCM allowed students with scores of 115 or higher to go into an advanced stats research design class, how many of these students would have that option? Can we have 0.74 of a student in a class? No, we can't. So to answer this question, we need to look at our data and make the best decision. So if you were the administrator doing this, how many students would you let into that class? You can make an argument for 2 different answers, but for this, I would probably round up. If I want to give probably 32 students the opportunity to take that class, because I don't want to take that opportunity away from a student who is super close to it. And we're just trying to make placement decisions. So I think with that, you would really need to pay attention to what you're doing and what you're wanting to get from the problem, because sometimes numbers don't make sense if there's a decimal. All right, so let's go on to our next example, example 2, and where we'll extend this even further. So we're doing the same problem, but the only thing that's different is what we're looking for. So the first part on our worksheet is the same as the first. We're using the same numbers, but the part that's different is the second part. So for this one, if UCM decided that students with scores under 80 had to take another basic mathematics course before taking the regular stats class, how many of these students would have to do the remedial course before taking stats? So typically, and I didn't do this last time for it, but anytime I'm solving a problem where I know I'm going to use the normal curve, I'm actually going to draw it out. I'm going to draw out a normal curve. I'm going to usually put the mean in the middle there, so I orient myself. And then I'm going to look at the information that I have in the problem. So here we see that our sample size is still 200. What is our symbol for sample size again? If you said lowercase italicized n, you're correct. So you'll see I'll put that information on there. I see that our mean is 100. So I'll put X bar equals 100. And then our standard deviation is equal to 15. And then our X value, we'll see X is equal to 80. So I'm going to label that on to our curve. And so when you label everything, it makes it a lot easier to visualize how we're going to do these problems. So where I have that 80 score, because I know that's the X score that we're looking at, sometimes I'll draw a full line so that we can see what we've got. So here it's saying a score of 80 and below, or scores under 80, the students will have to take that test. So what we have to decide now, are we looking for the area between the mean and Z or area beyond Z? Go ahead and shout the answer out loud. Answer this before moving on. Do we want the area between the mean and Z, or do we want the area beyond Z? We said we're looking for the area beyond Z for this one. You're absolutely correct. What's our first step going to be now that we have our normal curve all labeled? What do we need to find first? If you said we need to find the Z-score that's associated with the X value of 80, you're 100% correct. So go ahead and write your Z formula out. So Z equals X minus X bar divided by standard deviation of X. And then we'll go ahead and plug in all the information we have for that now. So we know that our Z is what we're looking for. We know our X value is 80 minus our mean, which is 100. And then that's going to be all divided by our standard deviation of X, which is 15. So when we write it out, this is what it should look like on your little worksheet. And then all you have to do is solve for it. So we take 80 minus 100, which is going to be negative 20, divided by 15. And what we're going to see with this is that when we take negative 20 divided by 15, we have a Z-score equal to negative 1.33. And then what do we need to do next? So we know what the Z-score is, but we're looking for the area beyond Z. Now that we have the Z-score, what do we got to do? You said we need that handy dandy worksheet you told me to print. You're absolutely correct. And so we'll use our Z table. Even though we have a negative Z-score, how do we use the table for that? What do we do? You said we need to go find just a Z-score of 1.33 because we're just looking at the magnitude or the absolute value of it. You're absolutely correct. So we go through on our Z table, we find a Z-score of 1.33. Here we're looking still for area beyond Z. And when we do that, what proportion of our data set falls beyond a Z-score of negative 1.33? So area beyond Z. Have you said the area beyond Z proportion equals 0.0918? You are correct. So now we know that 9.18% of our data set falls beyond a Z-score of negative 1.33. What's our next step? If you say we will multiply our proportion, which is 0.0918 by 200, you're correct. So let's go ahead and do that. So when we multiply 200 by our proportion of 0.0918, what do we get? We get 18.36. Students should take that class. If you're an administrator, what decision would you make? Would you have 18 students go in the remedial class or 19? You could probably argue either way, but if I'm an administrator, I'm probably going to require 18 of those students to take the remedial class because I don't want to make students take more classes than what they actually need to graduate, especially because how expensive tuition can be. All right, so we're going to keep extending this example, and we're actually using the same example again. So that's just the same basic information. We actually can go ahead and start labeling our normal curve with that information if we want. So remember, I always like to go ahead and put the mean there. We know our mean's 100, so it's right there in the middle. We know that we have 200 health science majors, so we're going to say N equals 200. We know our standard deviation of our data set's 15. And then let's look at the new information for this question. So if UCM decided to allow students with scores from 80 to 115 to take the regular stats class, how many of these students would have that option? You'll notice here, we actually have two different X values, right? We have an X value of 80. We also have an X value of 115. So what we can do for this is we can say X sub 1, our first X value equals 80. X sub 2 equals 115. We also will need to label that onto our normal curve. Okay, so I'm going to go ahead and label X sub 1 on my curve. So X sub 1 equals 80. And then on the other side, x sub 2 is going to equal 115. So I have my labeled normal curve with all this information that we have. And so how many of these students will have that option? So now what do we got to do? Because it's kind of a mess, right? We've not done a problem like this before. So in this case, because I have those two x values, I'm actually going to draw a line through the center of our normal curve, because we're actually going to find two different proportions. We're going to find the area under the curve that falls here and the area under the curve that falls here. Okay, so for this, you can really choose either one that you want to do. If we're looking at this, we're probably going to want to find those z-scores first, right? But the funny thing is we actually did this on the other page already, but you could already do that. You can do it again if you want. So if we're doing the z-score for x sub 1, the symbol that we'll use is we'll have z sub 1 equals. And then you would do the whole formula for that. So you would do 80 minus the mean, which is 100, divided by 15. We already did that and found that that equaled a negative z-score of negative 1.33. When we did the z sub 2 score, we took 115 minus 100 divided by 15, and we got that equal to a z-score of 1. So if you remember, we already did all that work. We're using the same example. And so we know that for our x value of 80, the z-score associated with that is negative 1.33. That is because a score of 80, an x score of 80 is 1.33 standard deviations to the left of the mean. And then with the x sub 2 value of 115, we know that the z-score for that x value is 1. Okay. And so when we do that, and we label our normal curve, are we looking for the area between the mean and z, or the area beyond z for all of this? You said for both of them, for both of those scores, we're looking for the area between the mean and z. You're right. There'll be two different numbers, right? So we'll find the area between the mean and z for this one, and then we'll find the area between the mean and z for this one and find those proportions, because we're concerned about what percentage of students fall right here in the middle where they can take that regular math class or that regular stats class. Okay. So we look up the area between a z-score of negative 1.33 in the mean. And when we look that up, go ahead and do that first before checking your answer. We find that the area between a z-score of negative 1.33 in the mean is a proportion of 0.4082. So I'd like to write that down. Area between the mean and z equals 0.4082. So if we converted that into a percentage, we'd say that 40.82% of the data falls between the mean and a z-score of negative 1.33. We have to do it for the other side too. When we do that, we find that the area between the mean and a z-score of 1 is 0.3413. That should look very familiar to you, actually, because when we did where I told you earlier on a standardized normal curve where the same percentage of data falls between each of the z-scores, one of those z-scores was between 0 and a z-score of 1, and we saw that 34.13% of our data would fall there. So what would be our next thing? So we have what proportion of the data set falls between here and here and here and here. What would be our next step? If you said we had to combine those two proportions, you're correct. So we would combine the 40.82% with the 34.13%. And you can leave them in proportion form because actually that's what we're going to end up using to find our numbers anyway. So here you would have 0.4082 plus 0.3413. And when we do that, and when we add those all together, we get 0.7495. So we wanted to know how many students, what 75.95% of 200 students was. We would take 200 and multiply it by the proportion 0.7595. And what do we find when we do that? We find 149.9. So with this, if we're the administrator for this, how many students are we going to let take this regular stats class? If you said 150 students, you are correct. So approximately 150 students can take the normal stats class without the remedial math class. All right, so if we put this all together, we can actually go through and look at our results from page 1 or example 1, 2, and 3. We found that we're going to have 32 students who could take the advanced class. So let's go ahead and write that on our sheet here where how many students could take each. We found that about 150 students could take the normal stats class without any form of remediation. And then we found about 18 students needed to have that remedial math class first, so they would have a greater chance at being successful in stats. And so if we add all those numbers up, if we added the 32 plus the 18, we get 50, and then 50 plus 150 is 200. So we have placed successfully all of our students into their proper classes. All right, so we have another example. So example 4, and this one's completely different because I'm going to get a little tricky on you. I'm going to kind of mess with your thinking a little bit so that you are able to really understand what we're trying to get at here. And that's that there's data underneath our curve. So you can go ahead. And our example is, say we have 300 students who need to take a physics course because there's only one professor who teaches calculus-based physics. They give the students an exam where the mean equals 100 and standard deviation equals 20. So here I'm going to go ahead and draw out my normal curve, right? Because I know, hey, I got some information here. We know that our sample size is 300. What's our symbol for that again? If you said lowercase italicized and you're correct, we see that our mean or X bar equals 100. So I'm going to go ahead and label that in the middle because remember that the mean is going to be in the middle there. We know that our standard deviation, S sub X equals 20. So I'm going to go ahead and write that onto my normal curve as well. Okay, and so they said they decided that people with the top 30.15% of scores can take the class. What is the cutoff score to get into the calculus-based physics course? So there's a problem here. We've not done this yet, right? So we're looking at this and we're like, well, crud. We need to find what our X value is. But how do we do that? First, we got to decide, is our X value going to be on the right or left of our mean? So if we look at it, the problem again, we're looking for the top 30.15% of scores. So that means our X value is going to fall onto the right of our mean. And hopefully, when I'm showing you my paper, hopefully the screen's not inverting the image. So it's going to be to the right. So hopefully I'll see when this plays back if it did that for me. But what we have here, we also have some new information that we haven't seen before, right? We're starting to see who the top 30.15% of our data set are, right? So what information is that? Where do we find that? Or where does that go? If you said they gave us the area under the curve, you're correct, right? So we're saying that we want to know what the top 30.15% of scores are so they can take this class. And we know that the area under our curve. So let's write out our z-score formula. Or do we not? What do we do first? How do we get this information? So we have the area under the curve. I completely messed that up without trying to do it wrong. But like, how do we do that? How would we find our z-score? Do we have enough information to find it using the formula? So it wasn't a mistake. It's a learning opportunity, right? We don't, but we do have what? What do we have where we could figure out what that associated z-score is? If you said we have our handy dandy table, you're right. So hopefully you printed it out and you're using it along with us. So to find this, we have to determine, okay, so we know the area under the curve, but is it the area beyond Z or the area between the mean and Z? So if we see here, we're trying to find the top. So we're trying to go away from the mean. So we're looking for the area beyond Z. So we want to look for a proportion of 0.3015 in the area beyond Z. So we'll look at our little table. Okay, and we're looking for area beyond Z of 0.3015. And when we do that, we find that that is associated with the z-score of 0.52. Now, do we have enough information to plug things into our z-score formula? If you said we do, we absolutely do, but this time we have different information, right? So we know that our z-score is equal to 0.52, so we'll go ahead and plug that in for our z. Okay, and then we'll put equal. Do we know what our x is yet? If you said no, you're correct, so we'll just write x minus the mean. Do we know what our mean is? We do, so we wrote it down on our other thing. So our mean was 100, so we'll go ahead and substitute that for x bar, divided by our standard deviation of x, which we found was what? Was 20. So when you write that all out, this is what it should look like for you. And then we have to do some algebra. We have to solve for x. So to do that, the first thing we have to do is multiply both sides by 20 so that we eliminate the denominator. And then when we do that, we see that 0.52 times 20 is going to be 10.40. And we have 10.40 then equals x minus 100. Then we need to get rid of we need to get the numbers by itself and the x by itself. So we add 100 to both sides. So it eliminates it from one side and puts it on the other. Okay. And then when we do that math, we see that our x value equals 110.40. Okay. So what that means is that in order for students to take that class, they need to at least get a score of 110.40 to be in the course. So you might be thinking, when are we going to use this? Why is this important? I don't plan on doing education planning or coaching where I have to determine who makes a team or doesn't. We're actually going to use our understanding of this to help us determine what outliers are in our data set. So you can look at this lovely illustration that I made for you. So one of the assumptions or rules for some of the inferential statistics that we're going to be learning is that our data set is free of outliers. Okay, in order to do this, let's talk about this first. Why is this an assumption? Why do we want it to be free of outliers? He said because you remember that most of our formulas are going to require us to use the mean. You're right, and we know that outliers pull the mean toward the outlier and don't always accurately represent our data set. You're 100% correct. Okay, because we cannot calculate the mean with outliers in our data set. So now I will be able to tell you how we will identify what is an outlier. We'll actually calculate the z-scores for every x value in our data set. And if our x has a z-score of negative 3.29 or smaller, which is why I taught you about the smaller numbers earlier, or a positive 3.29 and higher, then we will consider that an outlier, and we cannot have that in our data set to do some of these analyses. This is a lot of information. Right now, you just have to remember why we have this criterion. So if the x value is 3.29 standard deviations away from our mean, it is very far away from the mean, and it's an outlier. And we have another assumption that we're going to learn too, and it's called our normality assumption. And this is a characteristic that our data set has to have in order for us to do some of the analyses that we're going to do. And this assumption is that the population that we pulled our sample from is normally distributed. Do we usually have access to the entire population data set? We don't, right? Inferential statistics, we're using a sample to approximate and make guesses about what's going on with the overall population. We don't usually have access to that. So if we don't have access to our population, what do we have access to? Our sample. Okay. So eventually what we're going to do is check to see if our data set is normally distributed or it follows the same shape of the normal curve. There's a couple ways you could do that. You could literally build a histogram and see if the bars look like they follow the normal curve shape. Or we can also use something called the Shapiro-Wilk test for normality to test to see if it's normally distributed as well. So that's what we have for this week. Please let me know if you have any questions. I know this is kind of getting into some harder content, so please feel free to use my office hours. People have been doing that already. And let me know if you have any questions. I hope you have a great week.